Hi class, we are on chapter 11.3. This is constrained optimization. So what we're trying to do is optimize a quadratic form subject to a constraint, right? So I want to find the maximum or minimum of a value of this function such that x, y, or z, right? So I'm going to have some sort of conditions, and so I need to maximize or find the max or the min subject to those constraints, right? So this is a very important topic in applications. You'll see some things here that are very similar to what you would see in Calculus 3. So this should be a fairly straightforward section for a lot of you guys. So hopefully it gives you another way of looking at some things that you are already familiar with, right? So in this section, again, right, just to repeat what we're talking about, right, we're going to focus on finding a max or min of a quadratic form subject to the constraint on our input vector, which we are calling x, right? So here's a theorem. So suppose that Q is a quadratic form that takes Rn and gives you out R. Okay, so it takes n terms and gives you out a single scalar value, right? And let's say it has the form Q of x is Q1 times x1 squared, some coefficient times x2 squared, and so forth and so forth. So if you notice, there are no cross product terms here, right? It's just the different elements of my vector x, each being squared, right? So again, this was the nice form for us because we're able to do a lot more work. It's a little bit cleaner, right? So there's no cross product terms. Let Qi and Qj be the maximum and minimum respectively, right? So that means that Qi is the max, right? Since it's first and second. So I'm saying Qi is the max, and I'm saying Qj is the minimum, okay? Out of all of these coefficients, right? So again, I and j is the index. I don't know which one is which, but I'm saying one is max and one is min, right? A common constraint that we have is that I do not want my input vector to have a length that is different from 1, right? Basically, I just want to look at what's happening 1 unit away from my center of my function, right? So we have the current ways of trying to find those values out, right? So the maximum, which is Qi, right, the first one in this two little series here, is going to happen at x is e sub I, the standard ith vector, right? The standard unit vector ei, where it's 0 everywhere except for 1 in the ith position, right? And the minimum is going to be the same thing, okay? The minimum is going to be x equals e sub j, the standard unit vector where everything is 0 except for in the jth entry, which will be a 1. Okay, so now what we have here is an image kind of in general, just kind of like showing what's going on here. Okay, so I have some sort of quadratic form. Okay, so it looks quadratic, right? Any cross section here is some sort of a quadratic, right? As you can see here, there's a parabolas, right? If I cut it this way, there's parabolas. The constraint is that I am a distance of 1 away. So I'm looking at the unit circle, right? So along the unit circle, what is my lowest and highest point, right? So my lowest and highest point, this central portion here on the origin is not the minimum that I'm looking at, right? That's the global minimum of the function, but it is not the minimum of the function subject to my constraint. My constraint is that I am a distance of 1 away from the center, or basically I'm looking at a projection of the unit circle onto, in this case, the xy plane. It could be any other plane depending on my quadratic, right? And subject to that constraint, to that projection, what is the highest output value I'm having along those coordinate pairs that I'm looking at, right? And that's just for this picture. Obviously, we're in Rn, right? So, you know, we can be in sort of any kind of dimension when we're looking at this. But, you know, for that example in this 3 space, that's kind of what we're looking at, right? So we're looking at the constraint that I'm one away. If we were in 4 space, then my projection would be a sphere in 3 space. And then, right, trying to wrap your brain around that would be a little bit rough. But that's kind of what we're doing here, right? So we have a constraint that we are a unit away. And subject to that constraint, what is the maximum and minimum value of my function? So let's go ahead and go over an example. Obviously, these examples will be pretty straightforward because this theorem that we give here is very, very easy for us to tell where the minimum and maximum are. I really just have to look at the coefficients to my function, right? So let's go ahead and do our example. Okay. So what we want to do is we want to find the maximum values of this quadratic form such that the length of my input vector has a length of 1, right? So really, again, all we're doing is we're looking at the maximum and minimum coefficients that we have since we have no cross product terms, okay? So just from looking, it looks like the largest value I have is 3 and the smallest value I have is -4, right? 3 happens in the first position, so the max is 3 at the input vector of 1, 0, 0, 0, right? The minimum is -4, and that happens at an input vector of 0, 1, 0, 0, okay? So let's kind of expand that idea a little bit. It's one thing just for me to say it and say, hey, you guys, this is because of this theorem, this is the value. But let's go ahead and verify this just a little bit so it makes a little bit more sense to you guys. So again, Q2 equaling -4 is the minimum coefficient, and that happens at the standard unit vector E2, right? So it's zeros everywhere except for in the subscript position, which is at the second input. Okay, and Q1 equals 3 is the maximum, so I'm going to use E1 again as my input vector. Okay, so let's do a little bit of verification here. Okay, so remember, this is because there's no cross product term. We will kind of show different cases as we go through the video, but for no cross product terms, it's very, very easy to find the maximum and minimum. Please don't mix up this method with the other methods that we're going to go through in the video. Okay, so for no cross product terms, this is how this works. Very straightforward. So let's take a look at my quadratic form here, Q of x. Okay, notice that if I were to change all of the coefficients to the max coefficient, that this function is bounded by this function, right? It's bounded by the exact same coefficients, but having 3's everywhere. There's no way for this function to be more than this function if all the coefficients, all the things that change that are multiplied times the input values are larger here, right? All the coefficients are larger, right? So it can be equal, but only when this is the only input and everything else is 0, because if you notice, everything else is taking away from my largest value. And then I have one thing that adds to this, but not very much, right? So this is true for every input value in R4, right? And notice that 3, this term right here, 3x1 squared, 3x2 squared, 3x3 squared, 3x4 squared. This is the same thing as me factoring out a 3 and getting x1 squared plus x2 squared plus x3 squared plus x4 squared. And notice what this is, right? This is that condition that x equals 1. Okay? All right, since the length of this is 1, this thing has to equal 1 because this thing square rooted equaling 1 means this has to add up to 1, right? So this is 3 times 1, which is my maximum. Okay, so this is always less than or equal to 3, and it's only going to equal 3 when this has a length of 1. Okay, so that's just a quick verification here. If you were to prove this in general, this theorem that we had here, you would prove it really just the same way that I sort of did a quick hand wavy verification here, right? The proof of this theorem for the max and min values here would follow suit with this. Okay, obviously you would not have actual values. It would be very generalized. Q1, Q2, Q3, up to Qn. And then you just, talk about the maximum and minimum values, right? So let's go on to our last example, right? So therefore, this is always less than or equal to 3, and it's only equal to 3 at this location, right? Now, obviously, this should be the next question in our minds. Well, what about when there is a cross product term? How does this change me finding the maximum and minimum, right? Okay, so let's go over a theorem that goes over this in the same way. So let Q of X be symmetric where it is formed by X transpose AX. So again, here A will be a symmetric n by n matrix. And suppose that A has eigenvalues, okay, lambda 1, lambda 2, up to lambda n, right, because we're in n by n space. And it's ordered, okay. So I'm putting this in order. Lambda 1 here I'm considering as being less than or equal to lambda 2, which is less than or equal to lambda 3, etc., etc. Right? Here we're saying v1 up through vn are the associated normalized eigenvectors to these eigenvalues. So again, they have been normalized, right? They're not just the eigenvectors, but they now have a distance of 1. So we normalize these vectors, okay? We'll have the same constraint, right? That my input vector here has a length of 1. Then we're going to have a maximum value for Q of X at lambda n, eigenvalue. And that is going to occur at its associated eigenvector, Vn, right? Same thing for the minimum. The minimum is going to happen at lambda 1, or the minimum value will be lambda 1, and that will happen at its associated eigenvector, v1. Okay. So let's do an example. We're going to find the maximum and minimum values of Q of X equals Q1 squared for X2 squared, X3 squared, and for X2, X3, subject to the length of X equaling 1. So again here, what's happening here is I have a cross product term. Okay. So what we need to do is we need to build our function here, our matrix A, right? Our symmetric matrix that is associated with this quadratic form. So we learned how to do that in the last section. So we're going to just do the same thing, right? So again, the square terms are the diagonal, and then the location of this gets split across the two A I23 and A32 terms. Okay. All right. So I got 1, 4, 1, 1, 4, 1, and then at 2, 3 and 3, 2, I split this cross product term in half, and so that's my symmetric form. Okay. So now what I need to do is very straightforward. I'm going to find my eigenvalues. Okay. The smallest eigenvalue, I find the normalized eigenvector. That's the minimum and where it occurs. For the largest eigenvalue, I find its associated normalized eigenvector, and that will be the max value and its location. Okay, so it's actually pretty straightforward compared to some of the things we've been doing in the last sections, right? So here, if I start to find my characteristic polynomial, I'm doing the determinant of lambda I minus A, right? So very straightforward. You see that there's a lot of zeros here, so I'll just do lambda minus 1 times this determinant, okay, which gives me a very nice term like this, okay. I can multiply out this inside, which gives me a very easy characteristic polynomial, which is easy to find my zeros, right? So my zeros are 0, positive 1, and positive 5 for my eigenvalues, right? And I have them in order. So obviously my min value then will be 0, and my max value will be 5. I just need to find the locations for those. So this lambda equals 1 term, I don't even have to worry about it. I don't need to find the eigenvector for it. I don't have to do anything. I just need to find the two associated eigenvectors for 0 and 5, and that's it, right? Because that's my max and min values. So for lambda equals 0, right, we know how this works. We plug in 0 for lambda, we set it equal to 0, we do our RREF form, right? And then we see that we have what our vector is going to be here, right? So again, it should be a dependent system. And so we can pull out our location very easily, right? So we basically have that x2 plus 1/2 x3 is 0. So you subtract that out and we can get our values we need here, right? We all should know how to do this at this point. But notice again, we need this to be normalized, right? So it should be very clear here that when you square both terms and add them together, you get 5, right? So we divide this by square root 5 in a second, I guess I didn't do it right away. And for 5, right, lambda 3 equals 5, we do the same thing. We throw 5s here, okay, and we set it equal to 0. So 5 minus 1 is a 4, 5 minus 4 is 1, etc., etc. Okay, reduce it down and get our locations. Okay, so again, both of these have a length of 5, right, or square root 5, I should say. So we need to normalize this, so we'll divide each of these terms by root 5. Okay, and so for the minimum, I'm dividing everything by root 5 here. Okay, and for the maximum, same thing, I'm dividing everything by root 5. So the minimum is 0, and it happens at this location, 1 over root 5, negative 2 over root 5, and the max is 5 at 0, 2 over root 5, 1 over root 5. And if you want to rationalize this, you can. At this point in life, in your math career, I don't care too much. I really get on my my calculus and algebra students about that, but it's really up to you if you want to normalize it or not, or I'm sorry, rationalize this or not, but you should definitely simplify it as much as possible. Okay, so now we come to the problem of what happens when maybe I don't want to have the length being 1. Or maybe I do want the length 1, but then I have other conditions as well, right? So right now what we're going to talk about is, let's say that I don't want a constraint of my input vector being a unit away, right? I could change it to being any distance away. That's actually very easy to change. But what if I want this to be a function, right? What if I want it subject to not a unit circle, but an ellipse, right? What if I need an elliptical distance away for whatever reason, right? Maybe I'm looking at orbits, for instance, okay? How do I deal with that, okay? So if the constraint is an equation, we're going to do a change of variables, right? We'll do what's called a U substitution. I know you guys are familiar with U subs. So this is a little bit different than the way they do it in your textbook, but it's pretty much the same thing. Okay, I need the substitution so that the length of my substitution gives me out a distance of 1, and we can do everything like we were doing before because that's what we're used to. Okay, so let's go ahead and do an example. Okay, so let's find the max and min of the values of the quadratic form. Again, I have a cross product term still, but instead of having a length of 1, I have 9x1 squared plus 16x2 squared equals 144. Okay. Now, again, when I had x equaling 1, we were looking at, where'd it go? A unit circle. Okay. So what's going on here, geometrically, sorry you guys, okay, this is an ellipse. Okay. This has the form of an ellipse, right? You can look at it. It looks like a circle. X squared plus y squared equals r squared. However, you now have weights on the different x squares and y squares. Again, we're using x1s and x2s here, right? But that stretches you in the x axis and the y axis, and then it also gives you some sort of a radius that's not 1, right? So this is an ellipse. This is not the proper form, the standard form of an ellipse, but this is an ellipse. Okay. So here I have a is 2, 2, right? Those are the square terms. And then for the cross product term, I'm taking this 10 and I'm splitting it over the position a1, 2 and a2, 1, right? Because it's symmetric. I need the length of u to be 1, where u is a substitution made here. Okay, so I need that u1 squared plus u2 squared being added together and then square rooted gives me a value of 1, right? And so again, that implies that this inside form here has to add up to 1. So we'll just not worry about the square root term and just worry about the two square terms adding to 1, which is very similar to what we were doing. Sorry guys, when we're talking about that over here, when I said that x squared plus x1 squared plus x2 squared plus x3 squared plus x4 squared has to add up to 1. That's because, well, if I take the square root of this to get out a 1, this has to add up to 1, right? So we don't have to worry about the square root part. We just need that we need the terms when I square them and add them together that they add up to 1, right? That's really the necessity for this to get a length of 1, okay? So we're going to start by making our right-hand side equaling 1, okay? So I'm going to take my constraint, because that's what I need to be equal to 1. And so in order to make it equal to 1, I'll divide everything by 144. So now if you look at this, this looks more like what you would be used to when you're talking about an ellipse, right? The standard form of an ellipse, okay? And that's what we have here. So I make the right-hand side equal to 1, and I do that by taking my constraint, and I divide everything by what I would assume to be the radius of a circle, but it's not a circle, it's an ellipse, right? So now I have this form, okay? So note again that this is an ellipse that we want to transform to a unit circle, right? So you can think about that. We've actually talked about that quite a bit. We actually talked more about taking a unit circle and then using a linear transformation to transform it into an ellipse, and then using that information to find the area of an ellipse. We did that way back in chapter 3 something. You could use a lot of that same information here. You can use a linear transform if you so chose to, instead of doing these u substitutions, right? Just think about that a little bit though. You kind of have to transform everything. That would be a nice little exercise for you guys to think about, is how can I use transformations to transform this whole space instead of doing it the way that we're going to do it. So if you want to have a little bit of exploration on your own, I highly suggest that you kind of play with that a little bit, right? So let's go ahead and go through this problem now, and then we can revisit what I just said, right? So we need a variable substitution such that the coefficients become 1 when we square each term, right? I need to replace this with some u1 and u2 so that when I square them, I get out this 1, right? So I need to start to make some substitutions. This is what I want. That's my constraint. So I'm going to say x1 squared equals 144 over 9 u1 squared. So what I'm doing here is I'm taking x1 and I'm basically saying I need this to equal u1 squared, right? This is going to be u1 squared and this is going to be u2 squared, right? Okay. So if I do that, I can solve for x1 by multiplying by the reciprocals. Okay, so I wish I had this all on one slide, but I don't, right? So if this whole thing equals u1 squared, okay, that's my first substitution, and this is, I say u2 squared is 16 over 144 x2 squared. So doing that, when I want to solve for what x1 squared actually is, I have to multiply by the reciprocal here, right? And that's basically just what I did. I just said let the first one be u1 squared, isolated x1 squared, finished solving for x1, right? So square root both sides, and I got 12 over 3 u1, which means when I reduce this, it's really 4 u1. So x1 is really 4 u1. So I'm just making that substitution, and then I'm solving down for what x1 actually is. Okay, I'm going to do the same thing here. x2 squared is going to be equal to this. So you can really think of it as starting off by saying u2 squared equals 16 over 144 x2 squared, and then just starting to solve for x2, right, which will give me down to 3 u2. So if I take my constraint and I replace it with my substitutions, right? x1 is really 4u1 and x2 is really 3u2, and I square everything, I'm going to get 144 as my coefficients everywhere, which means I can divide everything by that and have my constraint of u1 squared plus u2 squared equals 1. So these are my substitutions in order to get the constraint that I want. Okay, so q of x, which is q of an input of x1, x2, now gets replaced with 4u1, 3u2, because that is what x1 and x2 is. I need to substitute in my new variables. So all of this stuff that I have here in terms of x, it all needs to turn into things in terms of u's, because I'm doing a u sub, right? Changing my variables from x's to u's, because the u's will be I created nicely to work well with what I need. All right. So plugging this into my quadratic form, instead of plugging in x1 everywhere and x2, I'm plugging in my u substitutions, right? So I'm going to have the following inputs. Okay, very easy to square. So 2 times 16 will give me the 32, right? 2 times the 9 will give me 18. And then I'll have 12 times 10, so the 120, right? So this is my new quadratic form in the world of u, right? Because I'm in variables of u now. So I have to redo my symmetric matrix, right? So I have 32 and 18 on the diagonals and 60s split across the other diagonal, right? The other terms, okay? And so now I can do everything that I need to do. This matrix has eigenvalues, right, that are the maximum and minimums of my functions subject to this constraint. So now that I'm in the world of u, my constraint equals 1. I've changed my my q of x matrix, right, my A matrix in terms of u. I can do all the math I needed to do before, and everything will translate over, right? So find my characteristic polynomial. Okay, it's going to give me this crazy thing. It 100% does not factor nicely, right? So again, I want exact values. Do not give me decimal approximations. Just throw it in the quadratic form and simplify it. Don't tell me that lambda 1 is at 1.239. I don't want that. I'm going to mark you down 100%. Okay, give me exact values and just make sure that they're fully simplified. So when I throw this in the quadratic formula, I get the following, right? 50 plus or minus square root, all of this stuff. I simplify it down and I'll get 25 plus or minus square root 3649, right? So the max value is the addition portion, right? And the minimum is the subtraction portion. So those are the exact values of my max and mins, okay? If I want to find the x value that's associated with each of these max and mins, I would find the eigenvectors of u with respect to lambda 1 and u of lambda 2, right, for these eigenvalues that I have, and then I would normalize them. So I will say this, I started to do that on my own, and these are just very, 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 very bad numbers. I did it by hand, obviously, because that's what I like to do, and it got really messy, so I'm not gonna make you do that or even watch me try to do that here. But we will do those, do the same thing in an additional example. Basically what you would do is after you find your eigenvectors here, you would need to do a change of variable back into the world of x, because right now I'm still in the world of u, right? So these are the max and mins, but when I get the eigenvectors, they're going to be eigenvectors in the world of u, so I got to change them back into x's, right? So that's just one thing that we would need to watch out for, right? So again, I'd have to normalize them and then change our variables back to x with these substitutions that I made at the beginning, right? So again, very, very, very messy for this example, so we're not going to do it because I really only wanted the max and min values for this example, okay? So again, I omit it for this example, right? So let's do an example where we do all of that work, Okay, change it around a little bit so it's nicer. But let's say that I have a rectangle that I need to inscribe inside of an ellipse. So again, I need a rectangle inside of an ellipse so that all four corners touch the edges of the ellipse, right? That's what it means to inscribe, in case you're not familiar or you're rusty with your geometry. This is the ellipse that I have, okay? I want to find the values of x and y that are going to maximize the area of my rectangle. I want my rectangle to have the largest area possible, okay? So here's an image of an ellipse with an inscribed rectangle. I have a formula for my ellipse, okay? So let z be the area of the rectangle that's inscribed inside of the ellipse, right? Then z is 2x times 2y, right? So you might be saying, why is it 2x, 2y? Well, I have a distance of x and another distance of x. So my length here is 2x, and same for the y, 1y, 2y. So 2x's and 2y's is the area of this rectangle, right? So again, for these application problems, you just kind of start to write down the things that you can figure out, right? So what I want to maximize then is this function. I need for xy to be as large as possible, subject to the constraints of the equation for the ellipse. All right, so now that I know what I want to maximize and what my constraint is, I can do everything the exact same way as I did for the last example, right? So I'll run through this a little bit faster. Okay, my A matrix has no square terms, so it is just the, if this was x1 and x2, it'd be easier to say, oh, okay, it's the 1 and 2 terms, right? So a1, 2 and a2, 1. Those are split for the coefficient here. And then we are going to take our substitutions as x is 3u1 and y is 2u2. So again, you know, you might notice the pattern here, right? But again, in order to find this, I divide everything by 36, okay? This turns into 1 over 9. This turns into 1 over 4 when I do that. And then I say, okay, u1 squared is 1 over 9 x squared. And then when I set that equality and solve for x, you know, I'll move the 9 over and I'll square root it. And that's why I get the 3u1. Same thing here. Okay, so I'm going to omit that work because it's fairly straightforward. I showed you on the last example. Just make sure you do the work as you go. Don't try to just jump to it, okay? And we'll substitute those terms in, right? And we can say, okay, this is going to give me 36, right? 3 squared times 4, 2 squared times 9. Everything will be 36. Now I have my constraint that u equals 1, right? The length of u is 1. So now I have to make that substitution into my function I'm trying to maximize, right? This is no longer the same function. This is an x and y. I need it in terms of u's, right? So I substitute 3u1 and 2u2 here, okay? And I got 24 u1, u2. So that's going to change my A matrix. I can write that as A sub u. And now I'm taking the 24 and I'm splitting it across the terms that it coincides with, right? So now this is what I need to find my eigenvalues for. Okay. Okay. So very easy to find. Split across my difference of squares. And so the max is going to be at 12, right? Remember I order them. So lambda 1 is the negative, lambda 2 is the positive, right? So the max area here that I can have is 12. And I need to figure out what input values give me the maximum area of 12 for my x and my y, right? So I'm going to find my eigenvectors here, okay? So I'm going to get, my system is going to reduce as such. This is going to be my u2, 1, 1, right? Because I got x1 equals x2, or u1 equals u2. I need to normalize that, okay? And then now that I've normalized it, I can make my substitution, right? I'm still in the world of u. I need to get back to these x's and y's that I had, right? So I know x is 3u1, right? So substituting in u1 is 1 root 2, right? 3 times 1 over root 2 is 3 root 2. Same thing here. My u2 was also 1 over root 2, so I have now 2 over root 2. And so my maximum is at 12. My maximum value is 12, and that occurs at x is 3 root 2, 2 over root 2, right? So I just got to change back into my original variables, and then I'll have my location, okay? So the last one we're going to go over is the orthogonality constraint, okay? So a common constraint, again, is to restrict that my distance is 1, and that my x vector is orthogonal to the eigenvector of the largest eigenvalue. Okay, so I need to have some orthogonality going on, right? So the theorem is that I have my quadratic form, A is symmetric, I have my ordered set of eigenvalues, they have associated eigenvectors, and these eigenvectors are orthonormal. So they're all orthogonal to each other, and they're all normalized, right? They all have a length of 1, and they're all orthogonal to each other, right? Then subject to the constraint that my input vector has a length of 1, I need my input vector to be orthogonal, have a dot product of 0 with the largest eigenvector, okay? Or, I'm sorry, the eigenvector associated with the largest eigenvalue, right? So the maximum value is going to be the eigenvalue before the largest eigenvalue, okay? And it's going to be attained at the eigenvector that is associated with it, right? And the minimum is still going to be the lowest, and it's going to be at its associated eigenvector as well, okay? So let's do a quick example, right? I want to find the maximum values of this quadratic form, subject to the input being having a length of 1, and that input being orthogonal to the largest eigenvector, okay? So this has no cross product terms, which is nice here, right? So this is what my A matrix will look like. This also tells me what my eigenvalues are, which is nice, right? So the eigenvalues are -5, -2, and 1 in that order, okay? The minimum value is -5. The max is not 1 because that's associated with the eigenvector I want to be orthogonal to. So the largest, the max here is going to be -2, right? And since there's no cross product terms, I know when they occur at, right? It's going to occur at E1 and E2, right? So -5 here is going to occur at its position, which is E3, apologies, right? And -2 occurs at its position, which is at E1, because that's where it is, right? And so my third eigenvector is E2, right? Because these are the eigenvectors. And that's the only time it's going to be 1, right? So all of these are orthogonal to each other, and they're all normal, right? They all have a length of 1. They're all unit vectors. And so that's it, right? So the constraints are met. They're all orthogonal to each other. They all have a length of 1. There's no cross product term, so it's very, very easy to find my solution here.